In this video, I'm going to do two subspace examples. In the first example, I've got this subset of the vector space of 3 by 2 matrices. Now first, let's make sure we understand what it means to be an element of that set. So I've gone ahead and written down a few examples. This one does belong to S because I need these two components to be 0. This one can be anything, but this one has to be 1 minus 2 times 2, which is 1 minus 4, which is minus 3. This one doesn't belong to S because this component's not 0, right? That component has to be 0. This one doesn't belong to S because it doesn't satisfy that property. This has to be A minus 2B. Now I want to show that this is a subspace of M32. The first thing I need is for the 0 vector to belong to S, and indeed it does. It satisfies the property to be in S. The 0 vector in M32 is just the 3 by 2 0 matrix. So I've gone ahead and written that down, that clearly that's in S. Next, I need to show that S is closed under addition. So I'm going to take two arbitrary elements in S. They have to be arbitrary. You can't take specific examples because you need to show it's true for every matrix in S. I'm going to take two arbitrary matrices in S, and I'm going to show that when we add them, we get an element in S. So I've gone ahead and I've taken two arbitrary elements in S. They have to be of this form. Now let's add them. Now when I add them, this is what I get. Now I need to make it clear that this in fact belongs to S. So let's go ahead and rewrite this component, this entry. So I've rewritten that entry of the matrix because I can clearly rewrite it in this way. And as you can see, I've got that entry is equal to this entry minus 2 times that entry. And that is the property I need, plus that those certain components are 0 for this to be in S. So I've got that it's closed under addition. The next thing I need to show is that it's closed under scalar multiplication. That's the third thing. So let's take a matrix. So here I've taken an arbitrary matrix. It has to be of this form in the set S. And I've taken a scalar alpha, which our scalars are coming from R. And I used alpha. I didn't use C. The reason I didn't use C is because I've got C in my matrix and I shouldn't be using a variable to mean two different things. Now I need to show that alpha times A belongs to S, and alpha times A is equal to that, and I need to make it more clear that this belongs to S, so I'm going to rewrite that one entry. So this is alpha A, alpha B, alpha A minus 2 alpha B, 0, 0, alpha C, and that's perfect because what I needed was for this entry to be alpha A minus 2 times that entry, and indeed that does belong to S, and we're done. We've shown the three properties hold, so indeed S is a subspace of that vector space. Now this example is a bit trickier. So for this one, we're given a fixed n by n matrix. We don't know what it is. It's just a fixed matrix. And we're told that the set W consists of all matrices, all n by n matrices that commute with X. So when you multiply A times X, you get X times A. And I want to show that this is a subspace of the vector space of n by n matrices. So the first thing I need to do is I need to show that it contains the 0 vector. And now the 0 vector in n by n is the 0 matrix. And we're going to write the 0 matrix like this. Okay, and this does belong to W. That's because, so to belong to W, the matrix has to commute with X. That's what this says. The matrix has to commute with X. So clearly it does because the n by n 0 matrix times X is just equal to the 0 matrix. which is equal to X times the n by n zero matrix. So indeed, the zero vector does belong to W. Next, I need to show that W is closed under addition. So let's take two matrices. Let's let them be A and B in W. And so what that means, if A is in W, it means that AX is XA for that fixed matrix X. And B in W, what does that mean? That means that BX equals XB. That's what it means to be in W. It means that you commute with X, right? So that's what that means. I need to show that A plus B is in W. How do I do that? Well, to show A plus B is in W, we need A plus B to commute with X. So we need that A plus B, when I multiply that times X, it's the same as doing X times A plus B. So that's what I need to prove, all right? So let's go ahead and do that. So we have that A plus B times X. Well, I know that matrix multiplication distributes over addition. So this is A times X plus B times X. But I also know, because I assumed that A was in W, that AX is XA, and because I assume B was in W, BX is XB, so AX plus BX is going to be XA plus XB, and now I can apply that distributive law again, pull out the X, and I get X times A plus B. And that is exactly what I needed to prove to show that A plus B belongs to W, right? A plus B commutes with X. So it's closed under addition. The third thing I need to show is closure under scalar multiplication. So let's let A belong to W. And again, what that means is that A commutes with X. And let's let alpha belong to R. Let's think about what we need to prove. We need to prove that it's closed under scalars, that W is closed under scalars. So we need to show that alpha A commutes with X. So we need alpha A times X is X times alpha A. That's what we are supposed to show. So let's go ahead and do that. So this is our proof in white. The green is just the part where we're thinking about what we have to do. So we have alpha A times X. Well, I know that matrices satisfy this property. And I know that A is in W because that was my assumption. What that means is that A commutes with X. So that's alpha X times A. And now I know that I can do the following. Matrices satisfy this property. That's X alpha A. So I just showed that alpha A commutes with X. So I can conclude that indeed alpha A belongs to W. And so I've shown that it's a subspace.